Hey guys, in this video we're going to talk about Chapter 15, Section 3, Constrained Optimization using Lagrange Multipliers. So in the last video we talked about finding absolute maxes and mins on of a surface on a region R. And we looked at examples where R was the entire xy plane. And basically what that means when we're talking about our region is we're talking about our domain. Since we're dealing with surfaces, our inputs are x and y values, right? We have two inputs. And so this was our domain. And with this, since the domain is the entire xy plane, that means that x can be anything. And y can be anything. That's what we call unconstrained optimization, when x and y are free to vary as they want. Now, if x and y are restricted in some way, then we have what's known as constrained optimization. So we looked at an example last time where we were optimizing on a rectangle. So we said, x could be between, I think it was 0 and 3. So we said x could be between 0 and 3, and y could be between 0 and 2. So we've imposed some sort of constraints on the domain. Okay, so that would be an example of constrained optimization. Okay, so this is going to be a little bit of jargon, but hopefully once we do some examples, it'll all come together and make sense. So suppose we want to optimize what's called an objective function. That's just a surface. Okay, so a surface with two independent variables subject to a constraint, g of xy equals c, and here c is a constant. Okay. So suppose p naught is a point satisfying the constraint g of xy equals c. F has a local max at p naught subject to the constraint if f of p naught is greater than or equal to f of p for all points p near p naught satisfying the constraint. F has a global max at p naught subject to the constraint if all values of f of p naught is greater than or equal to all values of f of p for all points p satisfying the constraint. Now this is just how we define these things, but let's talk about what this means a little bit intuitively. Okay, so here's the basic idea. I'm going to sort of try to give you the intuition by, to show you why the formula we're going to use works with this example here. So let's say we're trying to optimize, the basic idea is to find the max and min value of a surface subject to some constraint, subject to some restriction on the domain. Okay? And our surface is going to be of the form f of xy equals z. And we're going to have a constraint g of xy equals k, where k is constant. Now let's look at an actual example of a surface with a constraint function. Okay, so here we're going to consider the surface f of xy equals x squared plus y squared. And what this looks like, if you were to plot this on GeoGebra, it's going to look like a bowl, right? It's a paraboloid. Okay, so there's our surface, and we're constrained by the equation xy equals 1. What does that mean? Well, what that means is that the only values of x and y that we are allowed to plug in as inputs have to satisfy this equation. So for example, we can put in 1, 1. That would be valid. We can put 1, 1 into this equation to get an output of z. Okay, that would be valid. And actually, let's put it in. If we put 1 in here and 1 in here, we're going to get 1 squared plus 1 squared is 2. That's a valid point, okay? However, what would not be a valid point? How about 3, 6? That wouldn't be valid because 3 times 6 is not equal to 1. So this is not going to lie on our surface subject to this constraint right here. We have to have values of x and y that equals 1. Now, what about 2 1/2. Well, yeah, because 2 times 1/2 is 1, so this is valid, totally valid. If we were to plug in x is 2, y is 1/2 into this function, we would get z, right? We would get a z value, 2 squared plus a half squared, and that's going to be 4 plus a fourth, so 4 1/4 would be our output here. So that would be a valid point on this curve here, subject to the constraint. So hopefully that is making some sense, what the constraint function does, what points we can include, what points we can't include. And, okay, sorry, I had to cut that video. My cats were fighting. But anyway, so hopefully you guys are seeing the idea here. You know, this constraint equation is giving us our independent variables that we can potentially plug in to get outputs here. Okay, so now what I want to remind you of is something that we talked about a little while ago, and that is level curves, okay? So do you remember how we got level curves? So we had this surface. We had a surface, and basically what we did is we took that surface. So here our surface is f of xy equals x squared plus y squared. We took that surface, and instead of z, right, we changed that to k, to be a constant, right? So that we turned this three-dimensional problem and we smashed it down to 2D space. Okay, so we had k is equal to x squared plus y squared. We had k is a constant. And then, you know, we set this function to different values of k. So here in this picture, I have some level curves graphed for this guy. And those are in black. Those are the circles. So like the very innermost level curve is this guy right here. This guy, that innermost level curve, maybe I'll do him in green actually. Let's do him in green. This guy is just the circle x squared plus y squared equals 1. So I took k and I set it equal to 1 to get that level curve. Okay. The outer circle, like this, or the next most outer circle, I guess, this, I said x squared plus y squared, and then I set it equal to 2. And I kept going like that for a few times. There's infinitely many level curves that you could come up with here, but just to remind you of what they look like, they're right there. So I plotted some level curves there, and again, these are just telling me different values of z as I vary along x and y, right? As I move along x and y, what are my corresponding z values? Okay, so let's go ahead and look at our next slide and talk a little bit more in depth about what's going on here. Okay, so here is my constraint, okay, x, y equals 1. Now remember, points on our surface have to satisfy this constraint equation, right? We have to have x times y equals 1, okay? That has to be the case. So our constraint equation I have plotted in purple right here. As you can see, this xy equals 1. We have those two graphs, and the graphs are going to intersect our level curves at a certain z value, right? Okay, certain z value. Now, what z value is that? Well, it appears, one observation to note is that it appears the level curves of our surface intersect xy equals 1 at z equals 2. Right? Right, because this guy right here is representing z equals 2 as a level curve of our surface. Now, we can think of this guy as a surface in its own right? We can think of this xy equals 1 as a specific level curve on the function g of xy equals xy. Right? So this is a function, this is a level curve on the function. So the level curves are intersecting right here. And again, that is at a height of 2, right? That's x squared plus y squared is equal to 2. Okay, so let's talk about the big ideas here. So the first one, we can plot level curves for any surface. The surface we have here is z equals x squared plus y squared. We have some level curves plotted here. We have a constraint function, and we can consider the constraint function as a specific level curve for a surface g of xy equals xy. Okay, so this is a specific level curve for the surface right here. We can look at the picture and see that there are these two special points right here where the curves just touch each other. And at these 2 points, they either have the same tangent line, right? If we were to draw a tangent line to these curves at that point, they would either be the same tangent line, or they could be scalar. It could be a scalar multiple. The tangent lines could be scalar multiples of each other. But that's the idea: same tangent line at the 2 points, or parallel tangent lines. And let's bring back in the gradient here. Okay, so remember what the gradient was. The gradient was a vector that pointed in the direction of maximum ascent. Okay, so if we are considering this point right here, and we're thinking about which direction should I go to produce maximum ascent? Well, you're not gonna go this way or this way, right? Because the idea here is to get to a higher height, right, as quickly as possible, okay, as direct as possible. So these level curves, as we move out, that corresponds to bigger and bigger heights, right? We have a height of 1, we have a height of 2, a height of 3, and so forth and so forth. So as we move outwards, we're increasing in height. So the steepest ascent, the direction that we should go for steepest ascent is directly perpendicular to those curves, right? So it's gonna, look like this. We're gonna have a normal for the green curve, and then we're going to have another normal for the purple curve, our constraint. And these normals are going to be pointing in the same direction, right? They're just normal vectors. They're going to be perpendicular to those curves, and that is the gradient vector. That's the direction we should head in to maximize steepness, to maximize steepest ascent, because we're jumping directly to the next highest z value, if that makes sense. So the big idea here is that these guys, the constraint level curve and the level curve of x squared plus y squared, are going to have scalar multiples of, or their normal vectors are going to be scalar multiples of each other, okay? Or their gradient vectors are going to be scalar multiples of each other. That's the big idea here. And so that's number 4. So the gradient of f and the gradient of g are both perpendicular to f and g at the indicated points. Okay, so again, these guys here, that's the gradient. Okay, they're also known as the normal vectors because they're perpendicular to the curves at that point. And so this is what we've been leading up to, is this last piece right here. The gradient of f is going to be some scalar multiple of the gradient of g. Okay? this guy right here, this is lambda, and it is a scalar. Okay, so we're going to use this equation to do our constrained optimization problems. So let's take a look at our first example here. It says find the max and min of the surface we already talked about, subject to the constraint xy equals 1. So the first thing I like to do is I like to set up all of my equations. Now, what did we just say in part 5? We said the gradient of f is a scalar multiple of the gradient of g. So that's what we're going to use here. That's the big idea here. Okay, and this is the Lagrange multiplier. So how do I take the gradient of f? Well, remember what I did? I took partial derivatives and turned that into a vector, basically. So the gradient of f, if I look at f right here, the partial derivative with respect to x is 2x. So I have 2xi plus the partial derivative with respect to y is 2yj. Okay, so that's the gradient of f. Now the gradient of g, well, first of all, I'm considering this a level curve, but I want to actually consider the function who has this level curve, if that makes sense, to talk about gradients. So the function who has this level curve is going to be g of xy equals xy. So this is what I'm finding the gradient of. All right, so the gradient with respect to, if I take the partial with respect to x, I keep the first times the derivative of the second plus keep the second times the derivative of the first. So that's just yi plus xj. Okay. So now if I set up the equation like this, you know, for two vectors to be equal, their components have to be equal. And what I can do, actually, I forgot to do this, but I want to include the lambda in there, my little scalar multiple, just so that I can go ahead and set up a system of equations, okay? So here we go. Okay, so the components are equal, so I have 2x is equal to lambda y. All right, so I have the component of this equals the component of that. So that's one equation that I have. And I also have an equation, this guy, 2y, is equal to this component, lambda x. All right. And then my third equation, what I always like to write as my third equation, is my constraint equation that I started with, xy equals 1. Okay, so I have 3 equations and 3 unknowns, and I can solve this, okay? So I have a system of equations here. There's, it's hard to say, like, how to do these step by step because there's so many different ways that you can do this. My suggestion is to try to isolate lambda if you can, okay? So for instance, in this first equation right here, if I divide both sides by y, which you can do, and you should think to yourself, why can I do that? Because, well, I'm allowed to divide by y because y is not going to be 0. Why is y not going to be 0? That's a good thing to think about. But anyway, that's a side point. If I isolate to get lambda by itself, I get lambda equals 2x over y. Okay, so that's what that equation gives me. And over here, if I isolate lambda, I'm going to get lambda is equal to 2y over x. And, the whole idea here is I'm trying to find x and y, and when I get x and y, it's going to give me the max or the min for that, subject to that constraint. So there's not going to be any question about it. It is going to be an absolute max or an absolute min subject to that constraint. We just have to figure out which one it'll be. Okay, so anyway, I have lambda, and what I can do here is, since both of these things equal lambda, I can set them equal to each other, all right? So what this is going to imply is that 2x over y is equal to 2y over x, right? Lambda equals lambda, basically. Now what I can do is I can solve for one of the variables. You know, I guess I can just cross multiply, make that easier on myself. 2y times y is 2y squared equals 2x times x is 2x squared. I can divide the 2 out as well, and I get y squared equals x squared. And then if I take the square root of both sides, I get x is equal to plus or minus y. Alright, so there is my relation. X is equal to plus or minus y. So we have case 1. So we have case 1, we have x is equal to y. And then case 2, we have x is equal to minus y. Alright, so if x equals y, well, I see an equation that just involves x and y, so let's use that one. When x equals y, I'm simply plugging in y in the replacement in place of x. So I get y times y equals 1, which implies y squared equals 1, which means that y is going to be plus or minus 1. Okay, so y is going to equal plus or minus 1 in case 1. All right, and in case 2, if I plug in negative y in for x into that second equation, I get negative y times y equals 1. So that tells me negative y squared equals 1. Dividing both sides by the negative, I get y squared equals negative 1, but I can't take the square root of a negative number, so that is undefined, so we can just kind of cross case 2 out. Okay, so case 1, we have y is equal to plus or minus 1. So if y is equal to positive 1, then what's x? Well, we can use that equation again. So when y is equal to positive 1, we get x times 1 equals 1, so x is equal to 1 as well. Alright, so one critical point is x is 1, y is 1, and we're looking for z. We'll do that in a second. So that was the first one. Y was positive 1. Now let's do y is negative 1. When y is negative 1, again using that constraint equation down there, we get x times negative 1 equals 1, and so x is going to equal negative 1. Alright, so here's another critical point. So these 2 points, which we haven't found the z value yet, but we're going to in a second, but these 2 points are either going to be absolute maxes or mins subject to the constraint, okay? There's no, like, that's what's really nice about these problems. There's no question. There's no second derivative test. It's not like, you know, it could not be a max or a min. No, these are going to be maxes or mins. We just need to figure out which one. So let's go ahead and find the z value of both of these guys. And again, to do that, we can just use our surface equation that we started with. So our surface equation was fxy equals x squared plus y squared. So that's z, right? We got z equals, and that's what this third number is going to be. So z is x squared plus y squared. So first of all, we'll plug in 1, 1, and we get z is equal to 2. Okay. For the second one, again, we're going to get 2. We get z equals negative 1 squared plus negative 1 squared. So we get 1 plus 1 equals 2. Okay. So it turns out that we get the same either max or min. So this is either going to be a max or a min, both of these points, because they have the same z value. So it's either going to be the highest point or the lowest point, but we need to figure out which one's which. Now, how can you tell if it's an absolute max or an absolute min? Well, one way that we can deal with this is we can use the constraint equation. So the constraint says whatever inputs you're putting into this function need to satisfy x times y equals 1. That has to be the case. Now, it's we can see that these two guys satisfy that, but let's pick another random point, just a test point, so that we can identify if this is a max or a min value. How about we test the point x is 1/2, y is 2? Right? That works. If we plug in 1/2 for x and 2 for y, 1/2 times 2 is 1. That's definitely going to be valid inputs on our surface. So we're going to test these into our surface function. We're going to say, okay, well, what is f of 1/2, comma 2? Well, we get 1/2 squared plus 2 squared, and that's going to be a fourth plus 4. That's 4 and 1/4. And 4 and 1/4 is a higher value than 2. So it must be that these guys are the absolute minimums, subject to the constraint xy equals 1. Pretty neat, right? Okay, so here we go. Our final answer. I know that was a lot. And typically these problems aren't the easiest, so, don't feel bad if you're struggling with these. It does take a lot of practice. These are the absolute minimum subject to our constraint xy equals 1. Now, it's not the absolute minimum for the whole function, right? Because, we could see if we graph this thing would have a vertex at the origin. 0 would be the absolute minimum if we considered all xy values. But we are subject to a constraint here. So that is going to be our absolute minimum subject to the constraint. Both of those points will be. Okay. All right, so let's try another problem. Okay, so find the max and min subject to the constraint. So we always start off with our gradient equation. We have the gradient of f. Maybe I'll do this in black, actually. We have the gradient of f is equal to lambda of the gradient of g. So let's go ahead and find the gradient of f. So the gradient of f, so the partial derivative with respect to x is negative 2x. That's going to be I. Plus, with respect to y, is 2y, j. So that's gradient of f. Gradient of g times lambda. Well, gradient of g is going to be, well, first of all, this is a level curve. So let's find the actual function for g by just saying, okay, well, this is one z value. That's one level curve. So the actual constraint function is g of xy equals a fourth x squared plus y squared. And we want to take the partial derivative of this guy. So with respect to x, that's going to be, well, 2 times a fourth is a half. So that's a half x I. And of course, we have the lambda in front. Plus, I forgot the lambda again, lambda 2yj. Alright, so now we can set up our system of equations and do some fun with that. So, alright, so again, the components, following this equation right here, our components are going to be equal. So the I components are equal to the i's. These guys are equal. So we have some systems of equation. The first one we have is negative 2x equals lambda times 1/2 x. Okay, that's coming from the I spot. The j spot, we have 2y equals lambda 2y. And finally, my constraint is this one. We have a fourth x squared plus y squared is equal to 1. Okay, so we got 3 equations, 3 unknowns. Again, I like to see if I can get lambda by itself. That's kind of a general strategy that you can use. So let's go ahead and do that. Okay, the first thing I want to recognize in equation 1, though, and you might be tempted to do this, you might be tempted to divide both sides by 1/2 x to get lambda alone. And that assumption, what you're implicitly assuming is that x can not be 0. What you're implicitly assuming is that x cannot be 0. However, x is allowed to be 0 here. There's no problem there. In this problem right here, x couldn't be 0 because of this constraint equation, right? 0 times what is 1? Well, there's no such thing. So anyway, x can be 0, so we can't exactly do that, even though you might want to. What I can do, though, is I can add 2x to both sides, and when I do that, I get 0 equals lambda 1/2 x, and then plus 2x. And so what I can say here is, well, I can factor out an x. If I factor out an x, I get x times lambda 1/2 plus 2. Okay? And now, at this point, I can set each of these guys equal to 0. So when I do that, I get that either x is equal to 0, or when I set this thing equal to 0, I get lambda times 1/2. Oops. Maybe I'll just write as lambda over 2. Hopefully that's okay. This guy's lambda over 2 plus 2 is equal to 0, and I can go ahead and solve for lambda. So lambda is equal to -2. So lambda over 2 equals -2, then multiply by 2, so lambda is -4. So equation 1 tells me that x is 0 or lambda is -4. Fine, whatever. That's cool. Okay, so that's the information that equation 1 gives me. So we want to take into account the case that x is 0 and the case that lambda is -4. Now let's go ahead and look at equation 2 and see what information it gives me about lambda. Again, doing the same thing, you don't want to assume that y is non-zero. There's nothing in our equation that tells us y can't be 0. So we want to do the factoring strategy again here. And what I'm going to do instead is I'm going to subtract 2y from both sides to give me lambda 2y minus 2y is equal to 0. Then I'll factor out a 2y, leaving me with lambda minus 1 on the inside equals 0. Setting these guys equal to 0, I get y equals 0 and lambda equals 1. Okay, so those are the cases that I'm going to consider here. All right. Okay, so let's look at what happens when x is 0 first. Okay, so when x is 0, using my constraint equation down here, I'm trying to figure out information about y, right? Because if I have x and y, I have my max and my min. So when x is 0, I get 1/4 times 0 squared plus y squared equals 1. That goes to 0. And then if I take the square root of both sides, I'm going to get that y is equal to plus or minus 1. Okay? So when x is 0, y is plus or minus 1. We have y is equal to plus or minus 1. And we can list that as, these are critical points. Right, we have 0, 1, and then some z, which we're going to find later. And then we have 0, -1, and some z that we'll find later. And that's going to be a potential max or min. Okay? All right, so that was the case when x was 0. Cool, awesome. What about the case when lambda is equal to -4? Well, let's see. When lambda is equal to -4, which equation should I use to get some information? Well, I don't want to use this one because that's how I derived this, right? I don't want to use the equation I derived it from. The other equation that involves lambda is this guy down here, so I'm going to use it. When lambda equals 4, I get 2y equals negative 4 times 2y. Alright, so I get 2y is equal to negative 8y. And then I'll go ahead and add 8y to both sides to get 6y equals 0, and therefore y is equal to 0. Okay, so when lambda equals negative 4, we get the conclusion y equals 0. Well, when y equals 0, we need to figure out what the corresponding x is, right? So when y equals 0, I'm going to plug in that into my constraint equation to see what that's telling me about x. So I'm just plugging in 0 for y into my constraint equation. And I get a fourth x squared is equal to 1. Let's go ahead and multiply 4 on both sides to get x squared is equal to 4. And finally, taking the square root of both sides, I get x is equal to plus or minus 2. Alright, so that tells me when y is 0, x is going to be plus or minus 2. So that's some other critical points here. So we said, okay, well, when y was 0, x was plus or minus 2. So we have minus 2, 0, some z value. And then we have positive 2, 0, some z value. So that's another critical point there. So that was the case when lambda was equal to negative. Now I'm losing track. Negative 4. Okay, cool. So we took care of these two cases. Now let's look at these cases down here and we'll be done. Well, actually, we already covered the case when y was 0 here, right? We already looked at that, so that was kind of taken care of already. But what about what happens when lambda is equal to 1? Okay. Now let's look at the case when lambda is equal to 1. Which equation should I use to get some information from that? Well, keep in mind that I derived this from the second equation, so I don't want to use that one. I want to use the first equation because that one involves lambda, and I did not derive lambda equals 1 from that one. I derived it from the second one. So I'm going to use this one. I'm going to say, okay, well, let's see. Lambda equals 1. We have negative 2x equals lambda 1/2 x. And I'm going to plug in 1 for lambda. So I have negative 2x is equal to 1/2 x. Multiplying both sides by 2, I get negative 4x equals x. Adding 4x to both sides, I get 0 equals 5x. And then dividing both sides, I get x equals 0. Okay, but I already covered that here. I already found out when x is equal to 0, so this is kind of a redundancy as well. We already covered that. So all cases are exhausted, okay? So we found our critical points. There's 4 of them, okay? All of these, the 2 in red and the 2 in purple. And we want to see what our z values are because remember, these are either going to be maxes or mins. We're not sure which ones yet, but they will be, okay? So let's see. What was our surface function? Our surface function was z equals, let's see. Oh, y squared minus x squared. Y squared minus x squared. So if I plug in these guys for my critical point, so if I do f of 0, 1, I get 1 squared minus 0 squared is equal to 1. So that guy is 1. If I do f of 0, negative 1, I get negative 1 squared minus 0 squared, again, is 1. So these are going to either be the max or the min. We're not sure. But what's going to tell us is this next part, right? And then we'll use process of elimination. Okay, so what about f of negative 2, 0? Well, f of negative 2, 0, if I plug in negative 2 for x and 0 for y, I get 0 squared minus negative 2 squared. And that's going to give us negative 4. Okay, so that's negative 4. And then if I finally plug in 2, 0 into my function up here, I get 0 squared minus 2 squared is also equal to negative 4. Okay, so these are the same. That's either going to be a max or a min. This is either going to be a max or a min. So which is which? Well, this is the smaller z value, so this is going to have to be the min. All right, so both of these points are the absolute minimum, subject to the constraint. And this guy right here is going to be the absolute maximum. And that is our answer. Okay, so we want to find the max and min values of the surface subject to this constraint. So the first thing you want to do is set up your gradient equations. We have gradient of f is equal to lambda, some scalar, times gradient of g. So gradient of f, if we just take the partial derivatives here, with respect to x, it's just 1i, and with respect to y, it's just 1, then we have j. So that's our gradient of f. Our gradient of g times lambda is going to be lambda times something I plus lambda times something j. And so my g, if I take this to be a surface rather than a level curve, my g of xy is going to be x squared plus y squared, so that I can find the gradient of this. So the gradient, with respect to x, my partial derivative is 2x. With respect to y, it's going to be 2y. So now I can write my equations. I have 1 is equal to lambda 2x. And then I have 1 is equal to lambda 2y. And then I have my constraint x squared plus y squared equals 4. Okay. All right, so here, what I can do here is I can isolate lambda by dividing both sides by 2x and 2y. And the idea here is that, we can't have x equals 0 and y equals 0, right? That would be a false equation. So this is valid that we can do this. So anyway, if we isolate lambda, if we divide both sides by 2x, we get lambda is equal to 1 over 2x for that equation. And here we get lambda is equal to 1 over 2y. So if I set these equal to each other, I get 1 over 2x equals 1 over 2y. So I get 2y equals 2x. So I get x is equal to y. So this is my relationship that I have that I'm going to use with the constraint equation. So x is equal to y. So if I go ahead and sub in x for y into my constraint equation, I get x squared plus x squared equals 4. And this tells me 2x squared is equal to 4, which tells me that x squared is equal to 2, which tells me x is equal to plus or minus root 2. Okay, so then I can find the corresponding y values. So when x is equal to plus root 2, so let's see. We have x is root 2, y is going to be root 2 squared plus y squared equals 4. So we have root 2 squared is 2 plus y squared equals 4. So y squared equals 2. So y is equal to plus or minus root 2. Okay. But it's going to have to be it's going to only have to be positive root 2 because we have x has to equal y. They can't be different from each other. So we have x is root 2, y is root 2. Okay. So then when x is negative root 2, we have a similar story. We have negative root 2 squared plus y squared equals 4. And then solving for y, we're going to get y squared equals 2 again. So y is equal to plus or minus root 2. But again, x has to equal y. So when x is negative root 2, we have to just pick the negative version here. So we have x was negative root 2, and then y is also negative root 2. So let's go ahead and figure out our z's, because these are the critical points down here. These are the critical points. So again, to find your z value, you're just going to go up to your original equation, x plus y. So that was our surface. And so if I plug in that first critical point, root 2, I'm going to get root 2 plus root 2, which is 2 root 2. So that's my z value there. And then if I plug in negative root 2 into my function, I get negative root 2 is equal to negative root 2 minus root 2 is equal to negative 2 root 2. So since these critical points are the only candidates for maximum and minimums, it must be that the bigger one is the maximum, 2 root 2, and the smaller one is the minimum. Okay, so that's the absolute max and the absolute min subject to the constraint of the circle. All right, let's try this one. Okay. All right, so we have a surface, 2xy. We have a constraint, 5x plus 4y equals 100. We can think of this as a level curve, right, because we have the constant at the end. Or we can think of it as a surface, g of xy equals 5x plus 4y. Okay, so let's go ahead and use our gradient equations. We have gradient of f is equal to lambda of gradient of g. So gradient of f is going to be, all right, let's see. So the gradient of f is going to be the derivative partial with respect to x is just 2y. Partial with respect to y is just 2x. All right, so that's my gradient of f. Lambda times gradient of g. So if we take the gradient of g with respect to x, it's going to be 5i, and then plus 4j with respect to y. Can't forget our lambdas though. Okay, so now we set our components equal to each other to get our equations. All right, so the first one we have 2y is equal to lambda 5. Second one we have 2x is equal to lambda 4. And then we have our constraint. Our constraint was 5x plus 4y equals 100. Okay. All right, so this is going to be pretty straightforward, I think. To get lambda by itself, let's go ahead and divide both sides by 5 to get lambda is equal to 2 over 5y in the first equation. And then in the second equation, we get lambda is equal to 2 over 4x, which is 1/2 x. And then we can set these equal to each other. So we get 2/5 y equals 1/2 x. Okay, and then multiplying both sides by 2, I get x is equal to 4/5 y. So that's my relation. Now that we know that x is 4/5 y, we can plug that in here. So we get 5 times 4/5 y plus 4y equals 100. So then we get 4y plus 4y equals 100. So 8y equals 100. So y is 25 halves. Okay. Now what's x going to be? Well, x is 4/5 y. So x is going to be 4/5 times 25 halves, which is, let's see, 5, 10. Okay, so we got a critical point. So the critical point, there's only one. We have x is 10, y is 25 halves, and let's figure out what z is. So z is going to come from my original surface, which was this guy. F of xy equals 2xy. Okay, so I'm plugging in 10 for x and 25 halves for y. So I get 2 times 10 times 25 halves. And that's 250. So we're not sure if this is a max or a min. So we need to use a test point. And to find the test point, you can pull out your constraint. So we need a test point to see if it's the max or the min. It's going to be one of them for sure, but we don't know which one it is. So, okay, so our constraint says 5x plus 4y equals 100. So I need to find x and y values to satisfy this and just test it out to see if I get a number bigger or smaller than 250. So how about when x is 0, what could y be? Well, when x is 0, y is going to be 25. Let's test that point. So if I do f of 0, comma 25, I'm going to get, and remember I'm plugging this into my surface. My surface is 2xy. So I'm trying to see if there's a higher or lower z value than this. That's what I'm trying to do to see if that's the max or the min. Okay, so I have 2 times 0 times 25, which is 0. Okay, 0 is smaller than 250. Therefore, 250 must be the max. It must be the max. It couldn't be the min. If it was the min, this wouldn't make sense. We wouldn't get 0 for another test point. So this has to be the max. It's my max. Alright, let's try this one. So our surface looks like a circle centered at 1, -2. And our constraint is also a circle centered at the origin with radius √5. So let's go ahead and set up our gradient equations. So we have gradient f equals lambda gradient g. Okay, so the gradient of f, and I'm going to do these pretty quickly just because we've done plenty of practice with finding the gradients. Gradient of f is going to be 2 times x minus 1 I plus 2 times y plus 2 j. Okay, I just took the partial derivatives with respect to x and y. I had to use a chain rule, by the way, both times. And then lambda gradient of g is going to be lambda 2x plus lambda 2y. Again, I'm just taking the partials with respect to x and y. And this is I and then j. Okay, so I'm going to set my respective components equal to each other to get my system of equations. So I get 2 times x minus 1 equals lambda 2x. Okay, and then I have, let's see, I have 2y plus 2 is equal to lambda 2y. And then I have my constraint, which is x squared plus y squared equals 5. Okay. Alright, so let's go ahead and see what we can do here. So the easiest thing that we could do is we could divide by 2x and 2y. And that would make sense because both x and y cannot be 0, or that equation will not hold. So if I go ahead and divide by 2x here, I get 2x minus 2 divided by 2x equals lambda. And so that's just going to give me, lambda is equal to, if I separate the fractions out, I'm going to get 2x over 2x, which is 1, minus 2 over 2x, which is minus 1 over x. Okay. So there's lambda there. And then over here, similar story, I have 2y plus 4 equals lambda 2y. Divide both sides by 2y to get lambda is equal to 1 plus 2 over y. Okay. Alright, so we have lambda here, and we have lambda here, so let's go ahead and set them equal to each other. So we have 1 minus 1 over x is equal to 1 plus 2 over y. What I'm going to do to get rid of both of these denominators simultaneously is I'm going to do a little trick, multiply both sides by xy to get rid of those guys simultaneously. And when I do that distribution, I get xy minus y equals xy plus 2x. Alright, so then subtract away the xy's, that's cool. And then we get the relationship x is equal to negative 1/2 y. Okay, cool. So we have this guy. So let's use that in our equation up here. Okay, so x is equal to negative 1/2 y. So we have negative 1/2 y squared plus y squared equals 5. Just using my constraint equation and the fact that x is negative 1/2 y. So this is going to be a fourth y squared plus y squared equals 5. So a fourth plus 4/4 is 5/4 y squared equals 5. Let's multiply both sides by the reciprocal by 4 over 5. So y squared equals 5 times 4 over 5. So y squared equals 4. And therefore, y is equal to plus or minus 2. Okay? So in the case that y is positive 2, we get x is equal to negative 1/2 times positive 2, which is negative 1. So we have the point negative 1, 2, and then whatever our z value is. And in the case when y is negative 2, we get x is equal to negative 1/2 times negative 2. And that's just 1. So we had y was negative 2, x was 1, and we are looking for our z value here. So these are our critical points. Those are our critical points. So let's find our z value with our surface. So our surface is this guy. So we have f of xy is equal to x minus 1 squared. Was it x minus 1? Yeah, x minus 1 squared plus y plus 2 squared. Alright, so if I do f of negative 1, 2, get negative 1 minus 1 squared plus 2 squared. So that's 4 plus 4 squared is 16. So that's 20. Okay. And then for the other one, I have f of 1, negative 2. So that's 1 minus 1 squared plus negative 2 plus 2 squared. So that's 0. Yeah, that's 0. Okay, so which is the max or the min? Well, this one's higher. So that's the max. This is the max. And so this is forced to be the min, subject to the constraint x squared plus y squared equals 5. Alright, so let's use Lagrange multipliers to find the max and the min subject to the given constraint. So again, we're given a surface right here, and then we're given a constraint right here. So first thing, as usual, we're going to set up our gradient equations. We have gradient of f is equal to lambda gradient g. So the gradient of f is our gradient of our surface, so that's just going to be 3i minus 2j. And lambda gradient g, well, g, this is a level curve, right? Because we have this constant at the end. But if I think of this as a surface in its own right, it's g of xy equals x squared plus 2y squared. And so the gradient is going to be, well, with respect to x, we have 2x I plus lambda. With respect to y, it's going to be 4yj. So here comes our system of equations. We have 3 is equal to lambda 2x. Okay, we have negative 2 is equal to lambda 4y. And then we have our constraint, x squared plus 2y squared equals 44. Okay, so let's go ahead and solve these guys for lambda. So if I isolate lambda, I get lambda equals 3 over 2x. And down here I get lambda equals, if I divide both sides by 4y, I get negative 1 over 2y. So then I can set these two equal to each other. And I get 3 over 2x equals negative 1 over 2y. So then I can cross multiply here, and I get 6y equals negative 2x. Dividing both sides by negative 2, I get x is equal to negative 3y. Okay, so that's my equality there. So let's go ahead and plug in negative 3y in for x. Okay, so negative 3y squared is just 9y squared plus 2y squared equals 44. It's going to give us 11y squared equals 44. So y squared equals 4. So we get y is equal to plus or minus 2. Okay. So when y is equal to positive 2, if we follow this equation up here, when y is equal to positive 2, we get x is equal to negative 6. And when y is equal to negative 2, we get x is equal to positive 6. Okay, so those are the critical points there. So the first one we have x is negative 6, y is 2. We'll figure out what z is in a bit. And the second one, x is 6, y is negative 2. and let's figure out what z is. Okay. Alright, so let's see, what was my surface? 3x minus 2y. So we have f of xy, equals 3x minus 2y. Alright. So if I plug in negative 6, 2, I get 3 times negative 6 minus 2 times 2, negative 18 minus 4, it's negative 22. And then if I plug in 6, negative 2, I get 3 times 6 minus 2 times negative 2, so that's 18 and 4, which is 22. So that's going to be 22. So, you know, the higher one is going to be my max, and the lower one is going to be my min. It's my max, and that is my min. Okay, so we want to find the max and the min using Lagrange multipliers. Now this time, we have a function of 3 variables, so this is, you know, we're bumping it up a dimension, you could say that, but, you know, the process is just the same pretty much. So we have our, you know, we can think of it as a surface. It's not technically a surface in how we would imagine a surface, because we have that extra input variable, but that's the function that we're trying to find the max and the min of, and we have this constraint z is equal to x squared plus y squared. Okay, so how are we going to deal with this? Okay, so let's go ahead and, you know, first figure out what our gradient of f is, just like we usually would. So the gradient of f, we're going to take the derivative with respect to x, y, and z. Okay, so the derivative with respect to x, we have 2xi. Derivative with respect to y is minus 2yj. And then with respect to z, it's just going to be negative 2k. Alright, so what about g? Okay, so what we can do here is we can first subtract this z from both sides to give us x squared plus y squared minus z equals 0. Okay, so we can think of that as our level surface of g. And g of x, y, z is just going to be x squared plus y squared minus z. Okay. So taking the gradient of g and multiplying it by lambda, we get lambda something I plus lambda something j plus lambda something k. Alright. Okay, so if I take the derivative with respect to x, I get 2x. With respect to y, 2y. And with respect to z, minus 1. So now my system of equations, I get 2x equals lambda 2x. Okay. And then I get 2y is equal to, or sorry, let's try that again. Negative 2y, right, this guy equals lambda 2y. And finally, negative 2 is equal to lambda negative 1. Alright, so it's pretty, it's pretty straightforward to see what lambda is right here from our third equation. Oh, and we also need our constraint. I forgot about that guy. So let's go ahead and put him down here. We have x squared plus y squared equals z. Okay, so right off the bat, this third equation is telling me what lambda is. if I divide both sides by -1, I get that lambda is equal to 2. So that's pretty helpful here. Let's see. So, well, actually, is this helpful? If lambda is equal to 2, what can I say? Let's see. What can I say here? Well, if I plug in lambda equals 2 into this first equation, I get 2x equals 2 times 2x. So that means 2x equals 4x. And you can deduce here that x is equal to 0. Okay. We can do a similar thing here. If lambda is 2, we get negative 2y equals 2 times 2y. So negative 2y equals 4y. And I ultimately get y is equal to 0. Alright, so that's my critical point there. I get x is equal to 0, y is equal to 0. And then for z, I can use my surface, x squared minus y squared minus 2z. Oh, and also z is equal to 0, because if I plug in x is 0, y is 0 from our constraint, we're going to get z equals 0 as well. But we have this fourth piece right here because we bumped up a dimension. So let me put our line there actually. Okay. So this is our critical point. And if I plug in x, y, and z all equal to 0, my output is going to be 0 as well. So this is going to be 0. And the question is this a max or a min? Is this a max or a min? Well, we need a test point because we only have one point here. So how about we test another point subject to this constraint? How about, let's do x is 0, y is 1, z is 1. That is subject to this constraint, right? When x is 0 and y is 1, z is 1. That makes sense. So let's go ahead and test this point into our actual function up here. We get x squared, which is 0 squared minus y squared, minus 2 times 1. So that's just going to be 0 minus 1 minus 2, and that's going to give us negative 3. Now, negative 3 is a smaller number than 0, so it turns out that this critical point is our maximum. Okay, that's our answer here. That is our maximum point.